Okay, in example 5, we're talking about continuously compounded interest. So if you have $1,000 and it's invested at 6% compounded annually, then after 1 year, the investment is worth 1,000 times 1.06, which is 1,060. After 2 years, it's worth 1,000 times 1.06 times 1.06, which is 1,123.60 cents. And after t years, it's worth 1,000 times 1.6 to the power of t, since it's growing exponentially. Now, in general, if an initial amount is invested at an interest rate, R, for example, in this case, R is 6%, which is 0.06, then after t years, it's worth the initial amount times 1 plus R to the power of t. Now, usually, however, interest is compounded more frequently, say n times a year. Then, in each compounding period, the interest rate is R divided by n, and where R n times t compounding periods in t years, so the value of the investment is the following. You'd have the initial amount times the quantity 1 plus the rate divided by the number of compounding periods to the power of the number of compounding periods times t. So for instance, after 3 years at 6% interest, a $1,000 investment will be worth the following. So if we have 1,000 times 1.06 to the third power, that means that you'd have 1,191.02 with annual compounding, since that is representing as n. That would be when n is equal to 1. Now, if we said semi-annually, then that means that n would then equal 2. So in this scenario, we would have 1,000 times 1.03 to the 6th power, which is equal to 1,194.05 cents. Now, if we wanted to then invest quarterly, that would mean that n would equal 4. And so if we plug that into our formula, then we would have 1,000 times 1.015 to the 12th power, which is equal to $1,195.62. Now, if we go monthly, then that means n would then equal 12. And so we would have 1,000 times 1.005 to the 36th power, which again you can see it's increasing, gives you 1,196.68. Now for daily, then n would actually equal 365. So using that formula, you would have 1,000 times 1 plus 0.06 divided by 365 to the power of 365 times 3, which would give us $1,197.20. Now you can see that the interest paid increases as the number of compounding periods increases. So if we let n approach infinity, then we will be compounding the interest continuously. And the value of the investment will be the following. We would have a of t, which is equal to the limit as n approaches infinity, of the initial amount times 1 plus r over n to the power of nt. The next step is that we can then raise this entire function to r to the t power. We can factor out the initial investment, which is the constant a of 0. And then here we would have the initial amount where the limit as m approaches infinity, because now we've replaced m to be n divided by r, times a quantity 1 plus 1 over m to the m, all of it to the power of RT. But the limit in this expression is equal to the number e, as seen in equation 3.7.6. So with continuous compounding of interest at interest rate R, the amount after t years is a of t, which is equal to the initial amount times e to the RT. And if we differentiate this equation, we would get d of a over dt, which is equal to r times the initial amount times e to the exponent of rt, which would be r times a of t. So if you notice this formula, you would have seen that in prior algebra classes when we talked about continuous compounding. So in the scenarios that we saw before, these are specific. you're going to be using this formula because each one of these values of n is being compounded according to this formula. Now, continuous means that it's going to continue from n equal to approaching infinity, and that's why you have this formula for the continuous compounding of interest.